By this time, we have a deep understanding of the different types of bonding and how to draw molecules, covalent molecules, and all of the different types of properties. Now is where we start getting into the complexities of these Lewis structures and where we talk about their molecular geometries. And in furthermore, we're also going to talk about the polarity of these molecules and also what happens when a bunch of these same molecules get together and how do they interact. That's going to be pretty much the second half of this unit. So the first three were all about how do we build these structures. And now the second half of this unit is all about, now that we know these structures, how do they come together and how do they interact with each other? And we're going to start off in molecular geometry by exploring this objective. The student will be able to apply the postulates of valence shell electron pair repulsion theory, or VSEPR theory, to deduce the shape of a molecule and its resonance structures. Let's start off by defining valence shell electron pair repulsion theory, also known as VSEPR theory, and I'm going to continue to call it VSEPR theory because valence shell electron pair repulsion theory is way too much to say at one time. So, VSEPR theory states that each group of valence electrons around a central atom is located as far as possible from the others to minimize repulsions. Let's break this down a little bit. It makes sense. Think about valence electrons. Valence electrons are going to repel each other. So it makes sense that these guys are going to be located as far as possible from the other sets of valence electrons so that we can minimize those repulsions. I mentioned to you before about what a group is in this definition. Let's define what a group of electrons is. A group of electrons is any number of electrons that occupies a localized region around an atom. The following are all considered to be one, that's just one electron group. So a single bond, a double bond, a triple bond, a lone pair, and a free radical all are considered one electron group. This is very important. I understand that a double bond has technically 4 electrons in it, but those 4 electrons all occupy a single localized region, and so therefore they're considered a single or one electron group. So let's learn how to apply VSEPR theory through these steps. The shape of a molecule can be determined from a correctly drawn Lewis structure. That is so very important. You have to have a correctly drawn Lewis structure in order to get to the right molecular shape. It's just not going to happen if you can't draw Lewis structures. It's the reason why we spend so much time building these structures, because we have to do it correctly. So step 1 from our molecular formula is that we have to draw the Lewis structure. Once we have the correct Lewis structure, step 2 tells us that we have to count all of the electron groups around the central atom. Once I count all the electron groups around the central atom, that is what we know is known as the electron group arrangement. Step 3, I'm going to note the positions of any lone pairs and double bonds. That's going to lead me to information about my bond angles. And step 4, I'm going to count bonding and non-bonding electron groups separately. This is going to give me what we call the molecular shape. Now, I do want to tell you that in certain instances, the electron group arrangement or the electron group geometry may be the same. That can happen, and so you should not freak out or worry if that's the case. But I just want to let you know that the electron group arrangement and the molecular shape can be the same. Let's take a look at some examples, and what will help you throughout these examples will be if you have the chart provided in class that talks about the VSEPR sheet or the VSEPR theory sheet. That's going to help you out so much in being able to deduce the molecular shape. Now, as a side note, before I take a look at some of these examples, you will not be able to use that chart on any quiz, exam, anything. You have to have that guy memorized. So let's take a look at what happens here. In these examples, the only thing that you need to worry about is the central atom. And the reason for this is that the central atom dictates the shape of the molecule overall. So the central atom dictates the overall shape of the molecule. Let's take a look at this first example, BF3. So I'm only going to hone in on the central atom and what's happening. I'm going to completely ignore what's going on out here because it's not important. what is happening to that boron? That boron has 3 electron groups around it. Okay? Doesn't really matter what those electron groups are. So what the electron group geometry is, so I'm going to abbreviate this guy as the electron group geometry for this guy, is trigonal planar. In the next step, I have to survey the number of bonds and the number of lone pairs here. So for BF3, I have 3 bonds, and I've got 0 for the lone pairs. So that means its molecular shape is trigonal planar. Anytime that those 3 electron groups are 3 bonds and 0 lone pairs, that means that my molecular shape now is trigonal planar. In our next example, I'm again only looking at the central atom. The central atom dictates the overall shape of the molecule. So what's going on here? I have 3 electron groups around that sulfur. So that makes the electron group geometry trigonal planar. And because all of these 3 electron groups are types of bonds, that means the molecular shape is going to be trigonal planar as well. So as I said before, the electron group arrangement, or the electron group geometry, and the molecular shape can be the same. That's perfectly okay. Let's take a look at some more complex examples now when an atom has a lone pair on the central atom. So just taking a look at the central atom, it has 4 electron groups. Count them. 1, 2, 3, and 4. There's 4 electron groups around there. This makes its electron group arrangement tetrahedral, but now I need to survey the types of electron groups. What's going on there? The types of groups it has are 3 bonds and 1 lone pair. This makes its molecular shape trigonal pyramidal. Let's take a look at our last example. Only taking a look at the central atom, there are 6 electron groups around the central atom. This makes its electron group geometry octahedral. But when I survey these electron groups, there are 4 bonds and 2 lone pairs. This makes its molecular shape square planar. So for those of you that have had your chart next to you this entire time, you'll notice that it's the same steps over and over and over and over. Identify the electron group geometry, and then you'll notice on the chart, once you've defined the electron group geometry, you know that you have a certain amount of molecular shapes that it can be. We'll talk more about this in class through an activity, but I really want you guys to have an idea of how to garner the molecular shape using the VSEPR theory from the Lewis structure. Finally, we need to discuss resonance structures. Resonance structures are a way of describing delocalized electrons within certain molecules or polyatomic ions where the bonding cannot be expressed by one single Lewis formula. I think this is a really strong definition of what resonance structure is, but I don't think it really encapsulates the entirety of what a resonance structure is, and I much prefer this analogy. So think of who you are. Think about the kind of clothes you wear. Think about how tall you are and just how you picture yourself in your mind's eye. Now think of yourself as you would standing in a group picture with you and your friends. My question to you is, do you always look like this? Do you always look like what you're wearing in this photo? Are you always standing next to the people here, or are you always standing in that same location? And the answer for a good majority of us is no. You may be sitting down with your family to have dinner, or you may be going to the library to study with a group, or you may be going to the beach with some of these same friends, but you're not always in the same position. And the same thing is true for Lewis structures. They're not always sitting stagnant in this one pose or position. And a way for us to show these Lewis structures in their many different combinations and forms is through resonance structures. And this guy right here for CO3 2- is a perfect way that we depict these resonance structures. So each resonance structure is separated by this double-headed arrow, and that's just to show you that, hey, these guys are the same structure, but they're resonance forms. And essentially what happens here is it's just electrons moving around the atom. So where the double bond may be between this carbon and this oxygen, now in the next resonance structure it has moved over to this carbon and this oxygen. I haven't changed anything. It's not like I've changed the way the atoms are bound. I've just talked about how the electrons are moving around the molecule. So let's take a look at an example of SO2. So this is a perfectly great example of SO2 as a Lewis structure. But maybe is there a way that we could change only the electrons, never changing the arrangement of the atoms, but only changing the arrangement of the electrons and still get a different structure? And this is the answer to that question. This is a resonance structure of that same molecule of SO2, only the double bond has now changed its location. And here's yet another structure, resonance structure of the same molecule. Now, one final point about resonance structures. I cannot violate any of the rules that I have set up in this 4-step method that we have used to create or used to build Lewis structures. I can't violate any of those rules except for like expanding the octet. But this is allowable, especially in this example, because sulfur can expand its octet. It's allowed to do that. So you remember, you have to still obey the rules of VSEPR and valence bond theory.